Well, first things first, I just wanted to continue to encourage you guys because you guys have been doing a tremendous job under the most extreme circumstances. And just want to continue to encourage you and just say, wow, you guys are the work I've seen so far and the conversations we've had so far have just been tremendous. So, bravo and keep up the good work here. Because really all it is, it's about having great habits, day in, day out. We talked about consistency the other day. Just bring your focus, eliminate distractions, and create the best habits. And before you know it, you're going to be tackling the biggest bears that you can possibly tackle and doing it, rather effortlessly. So today, following on the heels of our discussion about different types of discontinuities, we're going to focus on continuity, specifically continuity at a specific point from a graphical perspective, and how do we prove it, right? So as we get into this, in fact, I'm going to start with the not so rigorous definition here. Our not so rigorous definition of continuity, I kind of call this my redneck version here. Can we trace the graph without picking up our pencil? So a lot of times you're going to look at a problem and you're going to instantly know whether it's continuous or not just by kind of, looking at it, inspecting it and, trying to determine whether you could trace it without picking up your pencil or not. But then trying to prove it is another case entirely different. And so we have this rigorous definition and we're going to really make this pop in our notebook. Okay. We really want this to jump out. So let's say we're going to prove that this function f of x is continuous at one specific point. And at one specific point, we're going to let it be x equals c. So, sometimes it might be x equals 1, x equals 5, x equals -2. But we're going to pick one specific value and try to prove that f is continuous. We have to check all three of these boxes. Number one, we have to prove that the general limit does exist, okay? And in that situation, if you remember from the other day, we're analyzing the function's intended height. Does the limit from the left equal the limit from the right? And if it does, then we have a general limit, right? Then we're going to check and see if f of c actually exists. And what we're measuring there is the function's actual height. In other words, is there a closed circle at x equals c? If you want to put that in parentheses here, actual height means closed circle, okay? And then step number 3 is we have to make sure that those first two answers we just got are actually equal to each other, okay? That the intended height matches up with the actual height. Oh, why did I write circle? Yeah, tell you what, not sure. So I should have said height there. So does the intended height match up with the actual height? In other words, does the closed dot fill the open dot? And if so, we've got a totally linked up and seamless graph that we consider to be continuous. All right, so we're going to try to practice this and kind of bring that to life a little bit because that always looks confusing when you first write that in your notebook. So here's what we're going to do. We are going to focus on proving whether this graph is continuous or not at x equals -2. So right out of the gate, you're like, there's no way this is continuous, right? Because you're tracing. It's continuous so far until we hit this point at x equals -2. We have to jump all the way down here. And so we've got a rather discontinuous function. We know the final answer is going to be discontinuous, but how do we document it? How do we prove it? So we're going to go through and try to figure out, we've got 5 conditions over here. And we're going to go through this list one by one, whoopsie daisy, and we're going to try to prove whether these are true or false, basically. Okay, so let's see, what is the limit as x approaches, well, what's going on? What is the limit as x approaches -2 from the left, okay? So if we're going to approach -2 from the left, I'm going to start in this neighborhood, and I'm just going to inch my way closer and closer and closer to -2. And it doesn't matter whether that was an open or closed circle, my answer is going to be +2 no matter what right there. Okay, so that's a +2. Now, what about the limit from the right? What if we approach -2 from the right? I'm going to start in this neighborhood here, and I'm going to inch my way closer and closer and closer to -2, and I'm approaching a height of -1. So let's say -1. Now you notice these two answers do not agree with each other. They disagree. So this general limit does not exist. Does not exist. Boom, right there. That right there, for all intents and purposes, we're done right there. Okay, if that limit doesn't exist, there's no way that this function can be continuous. It's impossible. but we'll practice the other two for fun. Okay, so when you get to f of negative 2, again, remind yourself, what are we measuring, right? What are we measuring? F of negative 2 is measuring the function's actual height. So all you got to do is look for the closed dot. Just look for the closed dot. It's sitting right there. So in this case, the answer is positive 2. Is the function continuous at negative 2? Of course, the answer is no. On your homework today, they're going to ask you to justify at this point. They're going to say, either justify that it is continuous or justify that it isn't continuous. And you've got a couple of options here. Basically, in this case, all I would say is that the limit as x approaches negative 2 of f of x does not exist. And right there, that is enough concrete evidence to justify that f of x is not continuous, okay? All right. Same graph, and we're going to analyze what's happening as x approaches 3, okay? What's happening as x approaches 3? Now, right out of the gates, my gut instinct, whoops, let me grab the highlighter here. My gut instinct is that the function is not continuous because when I get right here, I got to pick up my pencil, I got to dot that, I got to pick it up, come back here. And because I had to pick up my pencil to get around that hole, the function's not continuous. It's not continuous. But let's go through our checklist and see if we can document exactly why. All right. First thing we want to do is the limit as x approaches 3 from the left. So I'm going to start in this neighborhood. I'm going to inch my way closer and closer to 3. And we're approaching a height of 0. All right. Now let's take a look at the limit from the right-hand side as x approaches 3 from the right. So I'm going to start in this neighborhood, inch, 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 inch. What are we approaching? We are, once again, good news, we are approaching 0. So you'll notice these two answers do agree with each other. So this general limit here does exist. It equals 0. Now, here's the kicker. What is the value of f of 3? Look for that closed dot. You'll see that the value is negative 1. We've got a problem. These answers do not agree with each other. So is f continuous at x equals 3? And the answer is no. This time, my justification is I would just simply say the limit as x approaches 3 of f of x does not equal f of 3. So if you go back to that first, what we called our rigorous definition of continuity, and there was 3 conditions there. That third condition said that these two had to be equal to each other. Well, we violated condition number 3, and therefore f is not continuous. So basically, as you're going through that checklist, as soon as you violate one of those conditions, boom, all bets are off. You're done. The function's not continuous. All right. Let's see if we can actually find one that's continuous, right? Wouldn't that be exciting? I don't know if we're going to have any luck with that this time. We're approaching 4 from the left and the right. You know what? Let's do something different. Let's switch this up a little bit. Instead of approaching... Yeah. No, I'm going to stick with my initial plan. Let's do 4. Okay, let's do 4. So right out of the gates, I think as I approach 4 here, I had to pick up my pencil right here, right? I had to pick it up. So let's redo that. So I'm tracing, I'm okay. Whoop, got a hole, so I got to pick up my pencil and jump over the hole and continue tracing. So again, we kind of know the final answer. We know because of that hole, the function is going to be discontinuous. Let's go through our checklist really quick here. The limit as x approaches 4 from the left. We are approaching a height of 2. So we got a 2 there. All right, let's go back. Let's approach 4 from the right-hand side. Inch my way closer, closer, closer. Boom. We are once again approaching a height of 2. So we're good. The one-sided limits were in agreement with each other. So this two-sided limit, or this general limit, does exist. It equals 2. Everything's looking good so far. Well, the wheels come off here a little bit because now we're trying to evaluate the actual height, and you're kind of scanning this vertical column here looking for a closed dot, right? Well, we have no closed dot. So basically all that means is that f of 4 does not exist, doesn't exist. And because it doesn't exist, it's impossible for it to equal this number we had here. And so once again, we're going to say no, f of x is not continuous. And again, you got a couple of options, but you could just simply say f of 4 does not exist. Or you could say, you technically could say the limit as x approaches 4 of f of x does not equal f of 4. And they don't equal each other, because one exists and one doesn't exist. Either one would be a really great justification. So you'll notice our justifications are very simple, very concise today. We don't have to write any lengthy paragraphs. So unfortunately, I didn't show you an example of one that was continuous, but we could, a really interesting point would be this one right here at x equals -1. The function is continuous at -1. And so we could have gone through a very similar checklist and proven that f is continuous at -1, and we'd have been in great shape. So hope that helps. Doing a great job. Keep doing great work, guys.